Let's think about datums, and we'll start with surfaces as datums. You remember this idea that without datums, you have ambiguous instructions for inspection. And so we add datums so that our inspection is consistent. A datum is an imaginary place where measurements begin. They're where the measurements come from, and they are assumed to be exact. They are theoretically perfect. Datums are theoretically perfect imaginary places we take measurements from, but we establish them with real features on the real part. And the part surface stands in for the imaginary perfect datum. The datum feature is the feature on the part. So here, surface A is datum feature A on the part, and we set that on the surface plate. The datum simulator is the inspection equipment, the gauging equipment that we use to simulate the simulate the datum. Datums are theoretically perfect. Gauging equipment is not perfect because nothing is, but it is made to very, very close tolerances, and so that's why we use gauging equipment to simulate a datum from which we're taking measurements. If we're talking about a surface as a datum from which to take measurements, we can put this datum identifier, this suction cup thing, any place that is talking about a surface. So it could be on an extension line from the surface, or it could have a leader pointing to the surface. And like with all mechanical dimensions, the text stays unidirectional. It's always horizontal. Oftentimes, you will select three features that are at 90 degrees to each other. That's called the datum reference frame. That datum reference frame is three planes that are theoretically perfect and that are perpendicular to each other, and from which you will take measurements. That datum reference frame, those datum planes, are at a theoretically perfect 90-degree angle. The features on the part that you use to stand in for the datum features, they're not exactly 90 because parts are not perfect. We have a 3-2-1 rule when we put datums on parts. In a feature control frame, like you see here, the datum references, these letters, will go in some order. You often see ABC, but this could be anything else. It could be TQR, not in alphabetical order, not ABC. It doesn't matter. Any letters can go in here. But what does count is that the first letter, whatever it is the primary datum. The second letter is secondary. The third one is tertiary, which means third. The primary datum, in this case, surface A is datum A. So there's surface A. That's the primary datum because it's listed first. The primary datum is a surface. It has to make 3 points of contact. And think back to geometry. How many points does it take to define a plane? It takes 3 and only 3. So when you make 3 points of contact, there's no rocking, it's stable, and it's a surface. The secondary datum makes 2 points of contact. And here in the feature control frame, there's the second letter. It happens to be B. We see here that surface B is that datum. It is the secondary datum, and so it only makes 2 points of contact. And think about geometry. How many points does it take to define a line? It takes 2 points and not more. So what we have here is line contact with a secondary datum. The tertiary datum, tertiary means third, it's the third datum reference in the box. In this part, it happens to be a C, and here is surface C that is the tertiary datum for this part. The tertiary datum feature makes only one point of contact. So we have primary is 3 points of contact, secondary 2 points of contact, tertiary 1 point of contact. Now you have your part set up in a datum reference frame where all your measurements will be taken the same way every time. You could think about it this way. The primary datum supports the part. It's like setting it on a table. The secondary datum aligns the part. That line contact keeps it from twisting. And the tertiary datum, that 1 point, stops further movement. And you often see parts with only 1 datum or only 2 datums. You don't have to have 3. Now, this is related to degrees of freedom. And this relates to X, Y, and Z. When you're in a machine shop, you might see machines where they talk about, oh, this is a 5-axis machine, this is a 3-axis machine, so on and so forth. The axes are X, Y, and Z, and in jig and fixture design, a fixture holds a part so you can work on it. A jig holds it and allows you to drill. So jig and fixture design is tooling for manufacturing. And in this field, we talk about 6 degrees of freedom. When you're trying to restrict a part, you're trying to hold it motionless so you can drill a hole or take a measurement, you need to restrict movement in X, Y, and Z directions and rotation in X, Y, and Z directions. And if you do, that thing will be perfectly stable. Some people like to think about 12 degrees of freedom. They think of, okay, positive and negative X, positive and negative Y, and so on and so forth. So here's a picture out of a jig and fixture design handbook talking about the 6 degrees of freedom if you are stabilizing this part so that you can work on it. So first, think of this as being like the primary datum. 3 points of contact. These are not a very good drawing, but these are spherical tipped pins. So a spherical pin would make just 1 tangent point with the surface at each tip. So here are 3 points of contact. And that restricts 3 degrees of freedom, 2 degrees of rotation, and 1 degree of up and down movement. Then the secondary datum, or the 2 pins in your jig and fixture, restrict 2 more degrees of freedom. That's like your secondary datum. And 1 more pin stops the part from moving at all, and that is like 1 point of contact in the tertiary datum. So 6 degrees of freedom. Primary has 3 points of contact, secondary has 2 points of contact, tertiary has 1 point of contact, and here those datum identifiers are in order in the feature control frame. And that part fits into this theoretical, imaginary datum reference frame. The primary datum limits 2 degrees of rotation and a movement. The secondary datum will stop 1 more rotation and 1 more movement, and the tertiary datum will stop the final degree of movement. All right, datums. A primary datum, like we see here in this position control, here's datum A. That's the primary datum because it's in the first slot. So that means that datum feature A, here's A, looks like that bottom surface is datum feature A. It has to make 3 points of contact. Well, if you have a rough, bumpy part, that is not going to be too precise for taking measurements. So usually you will see some form control, like this flatness control, applied to the primary datum. That is known as qualifying the datum, but what it means is you make this thing smooth and flat so that it can sit down on your surface plate and make 3 points of contact. Datums don't have to be square, they can be any angle. So just to review, the datum is the imaginary place from which measurements are taken. It's theoretically perfect. The datum reference frame is those 3 mutually perpendicular planes that are theoretically perfect and theoretically 90 degrees apart. The datum feature symbol, or datum identifier, what I call the suction cup, is this little square here that identifies which feature is which datum. The datum reference is in the feature control frame, and here are the letters in order: primary, secondary, tertiary. On the actual part, the feature, the surface on the part, is called the datum feature. It's not perfect, but it stands in for the datum. Then the gauging equipment, or the inspection equipment, is called the datum simulator. It is not perfect because nothing is, but it's very, very precise. It's got very close tolerances, which we'll look at in a couple of days. We'll look at gauge makers' tolerances. They're very precise, so we can use this gauging equipment to simulate the theoretically exact datum from which measurement